Now it's serious. Welcome everybody to DLR Cologne. The workshop that we are having here today is part of a EU-funded project. Of course, we are grateful to the European Commission for Am I still presenting the screen? I don't know. Dominic, please give feedback in case of technical issues. I'm not fully aware, although I'm having here the screen. Yeah.
As long as
the
green block.
Now we're back. So we were away. Okay.
You were.
Okay. So what I will do, we have the cable now connected.
No, it's connected now.
So, but perhaps I should switch off the wireless. No risk, no fun. Are we still online? Yes.
Yes.
Okay.
Maybe ask Dominic whether she's still there.
You are still online.
Okay.
Okay. Just a short introduction on behalf of DLR for the three institutes involved here: Institute of Solar Research, Institute of Engineering Thermodynamics, Thomas Bauer, Institute of Future Fuels, Nicole, and somebody else. The DLR is not only in aerospace, but also in energy, in traffic, security, digitization. We're talking about energy, about controllable energy supply. Our works are from generation of energy or conversion of primary energy in wind turbines and solar, in particular concentrating solar, over intermediates. Thanks, Dominic. To the demand side, to the use. DLR is working in different institutes on this, and the slides are flipping forward and back. And the main source, in particular in our institute, Institute of Solar Energy, is the sun as energy source. It is the main energy source for the world, even if you compare it to all the other fossil energy sources, and it is one of the cleanest energy sources in the world. I showed this video already in a loop before, so I won't show it again right now. In the Institute of Solar Research, the focus is on solar heat production, on operation, on defossilization of the chemical industry, condition monitoring, and also a group working on districts and buildings. Although the technology in DLR has been we've been working on since more than 40 years in DLR. The origins go to the 70s for the first oil crisis. A specific Institute of Solar Research has been founded in the current form in 2011 with the directors Robert Pitzpal and Bernhard Hochschmidt, you know them. And we have additional requirements, including the solar tower in Jülich, the large Synlight solar simulator. In 2020, the spin-off of the Institute of Future Fuels, dealing with all the solar chemistry, fuels, and hydrogen. A second tower in Jülich for the many tests we are performing, and new department, sustainable supply, with Jana Stengler heading the department. We are in 5 locations: Cologne, here, Jülich, the solar tower, which is only less than 1 hour drive away. Stuttgart, on the university campus. Almeria, in a close collaboration with CMAT, Plataforma Solar de Almeria. And since a few years, Oldenburg, with infrastructure for coating and solar cells. Just a short view of the organizational chart, perhaps not so interesting for you. 3 main branches on concentrating solar technologies, on qualification, and as I mentioned, the new department with Jana Sustainability. And on the including Rainer, Luca, Daniel, and the facilities. A short view. Now we already have here the particle system site next to the tower, a heliostat field with more than 2,000 heliostats in Jülich. The molten salt platform in Almeria, operated by Pedro and his team in Evora. What was I saying? Sorry, Evora. I'm still too much Spanish. A nice picture of the same installation in Evora, with the heliostat collectors feeding into the molten salt system, and a large facility including several European Union projects, including also the supercritical carbon dioxide turbine coming up. That is now Almeria. The different solar fields since the 1980s operating there. This is still an older picture. We had some spin-offs of the institute. This is also interesting in the context of this project, that could be used as blueprint in different technologies. The Heliocon is now merged with the Synhelion. HelioHeat produced the particle receivers. LumoView and HeatBrain are in the building energy sectors, and Volatech doing the helicopter flights and automatic aviation. A few slides about engineering thermodynamics, Thomas.
Oh, yeah. We can come to the front. So my name is Thomas Bauch from the Institute of Engineering Thermodynamics. So the institute is located in Stuttgart, but we have also sites in Cologne. I'm also personally sitting here in Cologne, and the site in Hamburg and Ulm, and also Oldenburg. I think that's missing here. So the institute focuses on storage development, all sorts of storage, mainly also like electrochemical storage. We see 3 departments. They do the 3 departments you can see here. They do electrolyte, batteries, and fuel cells. And the department I'm working on is the thermal process department, headed by Annelies van der Sicken. She's based also in Stuttgart. Has about 50 people. And the next slide will show the department for thermal process technology. So the whole department purpose is to develop thermal energy storage solutions for solid media solution with Stefan Sumpf, for thermal systems with fluids. That's what I'm heading. Then we have a department for phase change material, and Andrea Gutierrez, and thermochemical storage with different materials. Yeah, this is in brief our work, and later on we will see some work of the thesis facility, and also do a tour to see the facility, because we operate it in our own group. I think I have one more slide for some event to make a bit of advertising. We have a Carnot workshop in Stuttgart in September. It's 3 days, 23rd to 25th. It will take place in the university, and we organize this together with the KIT. Thanks.
Yeah, thanks so much. So we're finishing the introduction on time. I hope you feel comfortable here. I hope the acoustics is good enough also for the online participants. Otherwise, please let us know. The feedback is difficult to get in these hybrid meetings. You all know that from your experience. I'm trying to monitor it a bit here on a computer aside, and Dominique is helping us. Thanks a lot, Dominique. It's a pity you could not come. Thank you for organizing it all. Can we put here one line once more? Can we see Dominic? Here's Dominic. Now we can see Dominic. The topics today are presented by colleagues from DLR and Enea in the morning, and also from Evora this afternoon, Radia and Pedro. Please let us make it an interactive workshop. Please ask, please interrupt us. Let's have a discussion. I think it's a workshop. It's a basis, hopefully, also for some other future collaboration. Be open. Don't hesitate to take electricity if you have enough supply, or coffee if you have enough supply, and water. Enjoy the day. Once again, thank you for coming. So, Christian, next. One last thing. My plan is to meet those who are interested this evening at Elzhof. This is a place close to the S-Bahn station. I hope you can make it. I'm planning hybrid beer. No, potential beer. So those who couldn't make it, you can still try to get to Bahn, S-Bahn, 6 o'clock in the evening. Let's meet there. I don't have resources to pay it all again, but I hope you come nevertheless. Welcome and enjoy.
Yeah, shall we check whether the camera is working as well? Yeah,
the camera is working. Yeah, I'm checking here.
Okay.
On the computer. So, das ist deine mit rotem Teil. Die erste, die hier, ne? Achso, ich habe hier auch so einen Knopf im Switch, wenn du möchtest. Funktioniert sogar.
Wow. Gut. Okay, darf ich hier stehen?
Ja, wenn du möchtest.
Okay, yeah, then thank you all again for coming and for taking a long trip.
Are we presenting?
Ja, ich glaube schon. Da oben ist doch dieses.
Ja. But here on the screen I don't see it. Dominic,
Can you hear us?
Are we presenting the slides? Okay, sorry, for some reason I can't see it here. You can continue.
Yeah. Okay.
Dominic shows thumbs up.
Yeah, okay. So, so the first talk today is about the prototype testing of our thesis facility. And just to pick you up, because very often people don't have the imagination what the thesis facility is. So thesis stands for Test Facility for Thermal Energy Storage in Molten Salts. And the plant is actually consisting out of two separate plants. So they are completely independent from each other, although it looks like it's one big plant. And we have one section which is called thesis store, where we do the testing of the single tank storage concept. And the second part of the plant is called thesis com, where the com stands for component testing. I will focus on the prototype testing we do in the store facility, because I will have some slides on some experiments we did with the other plant in the afternoon. Okay, so first, I mean, on the picture, it looks a bit complex with all the piping going up and down here. So this is a more simplified diagram of how the plant is actually looking like. So basically what we have is we have two reservoir tanks, a hot reservoir and a cold reservoir. This basically acts as a heat source or heat sink. And that is then providing us hot or cold salt to the actual test object. And in our case here, the test object is the single tank storage system. And so we can pump in hot salt here into the storage tank to charge it. And then the cold salt will be pushed out at the bottom and flowing back to the cold tank. And as we are testing a thermocline concept, which means we have a region where we have like a temperature transition, this also means that at some point there will be hotter salt coming into the cold tank, and therefore there's a cooler. And on the other way around, when we discharge, at some point the exit temperature will drop, and therefore we have an immersion heater in the hot tank to compensate for these temperature decline. So and then basically the inflow is from the top and the outflow on the hot side is here from the side, whereas on the cold end we enter and exit the tank both from the bottom. There's some kind of siphon here. The reason for that was that the cold tank is made of a different materials. So in case of any failure, we can make sure that there's no uncontrolled inflow of salt into the cold tank. And a feature of the plant is basically that we can have a pure thermocline in there. So meaning that we have only stratification of the salt just due to its density differences, but we can also test a concept where we have a filler material inside the storage tank, and to get the filler in and out of the tank has a total height of more than 5 meters. We can put the material inside 3 baskets we can stack on top of each other, and this allows us to prepare basically everything outside of the storage tank, and then finally when everything is ready we can put in everything inside the tank. It's a matter of a couple of hours and then we are ready to start testing. Here are some pictures. So on the left you can see a look inside of the storage tank. Then on the right you can see where we were putting the filler material inside of these baskets into the tank. So they have some large handles, and then we have an auto crane coming up and just lifting everything into the tank. And then here you can see the top of the tank after the 3rd basket was stacked in there. And then finally on top there's coming like distributor device for the salt to evenly spread the salt when it's coming from the top. You can also see somewhere here on the right, there's the outflow, and obviously we are putting in there a lot of thermocouples because it's our main interest to measure the temperatures inside of the tank. Now, what we are looking at is different single tank concepts. So starting from the state of the art, basically the 2 tank concept. The first concept we've been looking at was, or prototype we've been testing was the pure thermocline. So as I said, where you basically put both hot and cold salt together in one tank and have it separated just by density differences. So the hot salt is basically 10% lighter than the cold salt. So you can have some sort of separation and have a thin layer of this transitional zone between the hot and the cold. And in general, this obviously has some advantages because you have only one tank left instead of 2, with a lot of cost savings. less land consumption and so on. But you have a more complex system. I mean, the two-tank system has a very constant power output or output temperature. In this case, you have to deal with declining or increasing exit temperatures. And yeah, there's a slightly larger salt mass. It also depends on how much you have left in the sump. Here you have only one sump, here you have two. And another aspect is obviously you're not having a constant tank temperature. You're also dealing with temperature gradients inside the tank walls, which is also a topic which needs to be addressed. And then we have also two more advanced single tank concepts. The other one is the one with the filler material. There you can substitute most of the molten salt with the cost-effective filler material. This is a big advantage and the most potential for cost reductions. But you also have to deal with a larger temperature drop as you have a bigger thermocline in the system. And there's more topics you have to address. For example, if you have a packed bed, there is also thermomechanics you have to care about, of the movement of the packing. And also you need to deal with some filler and salt compatibility. And another concept we've been testing was the moving barrier concept, where you have basically a insulated floating barrier between the hot and the cold molten salt. And here the most challenging part is the design of the barrier itself. Okay, now let's have a look at the prototypes we've been testing. So the first one we've ever tested in the plant was the pure thermocline concept. So this was actually already the second prototype, bit improved. In the first experiment, we had some issues with failing thermocouples. And here the focus was also a bit different. So to test it, we have basically, we call it a thermocouple tree. So it's a metal structure you can insert into the tank, and you can attach thermocouples to it. And then you have the possibility, for example, to measure actual temperatures, but also what we did here, because in this experiment, we were less interested in the thermocline itself. It was more focusing on the near wall temperature field inside the tank. So therefore we had like a field, a two-dimensional field of thermocouples in this region. And so this was some results from the first experiments we did with the initial thermocouple tree. As you can see, there were a lot of thermocouples who apparently failed, but we were still able to measure the thermocline profile inside the tank. And you can see there's a very good stratification achievable. So this is more than 5 meters in height, and the thermocline thickness itself is way below 1 meter. So so the results we achieved were quite satisfying. And we will also maintain that for several cycles. And so this was more recent investigation, where we then focused on the temperature field in the near wall region, because the question was how stable will the thermocline be in terms of standby periods. And also what we were interested in was basically the difference between the thermocline profile inside the molten salt and also the temperature profile in the tank walls. Because when you do investigation of tank wall stresses and so on, you want to know what kind of temperature you have to expect. And all we typically know is the temperature field inside the molten salt and how that was linked to each other. yeah, that was also a video. So what we did here was we took the measured temperature values and fed this into a MATLAB two-dimensional interpolation and created a video sequence out of it. So it's not a simulation, it's just generated.
That has the same soil conditions and same type of foundations.
I'm sorry? Was that a question? Okay, and yeah, from this data, we were then able to create a two-dimensional animation of the temperature profile. And apparently, opposed to our expectance, there was quite a very homogeneous temperature stratification, even in the near tank wall region. So there was not a huge gradient to the outside of the tank wall. And then in a collaboration with the TU Ilmenau, there was a PhD candidate. He was looking deeper into the topic. So what he was investigating was like small recirculations happening in near wall regions. And you can, if these small recirculations are happening here, you would see some fluctuations in the temperatures. So you can measure temperatures anywhere. And if there's flow, you would have some fluctuations in the temperature. And these temperature fluctuations have a certain frequency. And by a frequency analysis, you can identify salient frequencies. And there's a theory behind this. It's called the Weserler frequency, which is linked to the flow velocity of these tiny fluctuations. And then from these frequency analysis alongside with the model behind that, you can then derive some sort of microscopic fluctuations. But we didn't see any large-scale recirculation, which is some sort of like salt is cooling down near the tank walls and then causing huge wakes of flow. So it was only on the micro scale, and in a large scale system, it's also less relevant. Yeah, then what we looked at was the thermocline with the filler material. We started off with a packed bed. So we had a basalt rock packing in a 8 to 11 millimeter grain size. That was tested in two projects. Here you can see the temperature profiles obtained on the initial charging cycle. And yeah, as you can see, still there's a very good thermocline possible. It's less or a bit wider than if you were having the pure thermocline. The reason is because there's also some heat transfer into the rocks, which is basically slowing down and widening the thermocline thickness. And as I said before, what we do typically in parallel is also investigations of material compatibility here. And we are also now focusing a bit on thermomechanics. So there's an effect called ratcheting. Basically, the tank is expanding when it's heated up, and then the packing can sink down. And in the next discharge cycle, when the tank wants to contract due to colder temperatures, then the packing might prevent it. And it's not really understood what is actually going on there and how the packing is moving inside the tank. And the last project we were having was the nuclide project. And here we were testing some sort of refractory bricks. So basically we had these kind of clinker bricks you can see here on the pictures. They were mostly inside the tanks. We also had one material from the project partners. There was only in the topmost layer. And yeah, we We had some ideas here, so we did some AVI wire mesh between the layers of the bricks. So in case there is some blocking of some channels in the flow, the bricks are separated on each layer. So there can also be some redistribution of the flow. And yeah, then we had a company who was cutting all the bricks and fitting them in the baskets. That obviously, if you go to a larger scale, you would want to have much bigger of these bricks, but in this project we were focusing on something readily available. And yeah, here I also have a nice video of the discharging cycle. You can see here, if you so that was just the first charging cycle. You can see here, if you compare it with the other results, the thermocline is getting a bit wider. That is because you have, particularly in the project, we didn't have the material which was the one we originally designed. It was more something available. But obviously, if you have like small rocks and flow around the rocks, then there's much more mixing and a much better heat transfer into the material than if you have like straight channels where the flow is going through. But in theory, the material, if you have not a packed bed, if you have the brick material, you have some advantages. You don't have the issue with the ratcheting, that the material can expand and contract, so it remains in its shape. And secondly, you can design much lower void fractions. If you have a packing of uniform grain size, you would typically end up in the region of 40 to 50% void fraction. You can get lower, but then you have to mix different particle size. So basically, you have to have huge particles, which then has 50% void fraction, and then you can fill all the gaps with smaller particles, which itself has also 50%, and then you end with only 25% void fraction. And then if you can also fill the remaining gaps with some sort of sand, and you can get down, but then yeah, you have big brick rocks and small rocks, and yeah, if you have bricks, pre-manufactured bricks, then things get much easier. You can have very tiny channels in the desired design. But on the other hand, it's obviously more handling effort and production efforts. And then we had a project which was called Mobile Climb, where we tested the moving barrier concept. So here are some pictures of this moving barrier during the commissioning. We did a lot of theoretical work initially. So on the left, you can see, for example, a standby simulation. And obviously, if you have a thicker barrier, which has more insulation, then there is less heat transfer through the barrier. But interestingly, when you look at the storage efficiency after cycling, then we found that you have the highest efficiencies basically with smaller barriers. And the outcome basically was that it's not the heat conductivity, it's the temperature conductivity is the most important factor here. So the temperature conductivity also contains the density of the material. So actually the ability to store heat of the barrier itself. And so that's why we actually ended up with a thinner barrier. And if you also think of it from a practical reason, thinner barriers are much easier to design. So if it's thin enough, then you just need to have some sort of insulation material inside, and then the steel of the barrier is adding enough weight for the barrier to sink in the hot salt, but to float atop of the cold salt. So the density of the barrier needs to be somewhere between the cold and the hot salt density. Otherwise, if it's too light, it will float atop. And if it's too heavy, it will sink down. And if you had a very thick barrier of, say, 1 meter in thickness, and you fill that up with insulation material, which is typically very lightweight, it would float. So you would have to add a lot of bricks in there to make it sink down. And yeah, so what we did was then, yeah, we designed the barrier. We had some thermocouples attached. We had this spring-like circular concept here for the thermocouples so that it can move up and down. We also had some steel rope attached to directly measure its position. And the issue we had here was we evacuated the barrier and then we closed it. But when we started operation, we found out that there was apparently still some sort of residue left inside, maybe water moisture, or maybe even, so we did a post analysis in the lab, even we found some carbon dioxide, so there must have been some reactions going on, and that caused the barrier to somehow blow up. And when we looked inside the tank, we found that it was floating. So we just came to the stage where we, heated up everything up to 400 degrees, and then we found out that the barrier was apparently blowing off. And the next time we found out you have to continuously remove any gas which might formate inside the barrier. So you could have attached like a small flexible hose or something to it, and then continuously pump out air of the system. Yeah, so that was my part from the prototype testing.
Danke.
Yeah,
Thank you, Christian.
I don't know if you have some time for discussion or.
Let's try to
2 minutes.
get some questions.
Okay.
I mean, I don't think 2 minutes are relevant. If there are no questions, we take 2 minutes. If there are questions, we should discuss them.
I have a question,
Yeah.
Klaus, you can one from that point. You mentioned at the beginning some advantages and disadvantages of thermal design compared to two tanks.
Yeah.
And one disadvantage is the temperature drop. Is there any strategy how to tackle this? If you like to have a more or less constant temperature, for example, oversize with thermal storage, and if so, what is the order to oversize it?
I think it depends on the application. So, for example, if you had an electric heater based system, you could use the electric heater during discharge for some sort of boosting. When the heater is already there, then you can discharge until you have your temperature drop, and then you have, obviously you need some electricity during discharging, but this would be one solution. And the other concept would be to have some sort of operation strategy. So this is a topic where you have to look a bit deeper. So the thermocline increase is typically caused by conduction and also by the limited heat transfer. So for example, if the rocks were like this, we go through there with salt, then there's very small heat transfer. You have this typically in concrete-based storage system where you have a very long flow distance. And the thermocline inside is a very wide one of 50 or 100 meters, or even it stretches over the whole system. And so yeah, by having small rocks and so on, the thermocline remains quite small. And if you keep the thermocline completely inside the system, it will grow over the cycles and over the days. And then at some point you end up with a huge thermocline spreading over the whole system. So you need to get the thermocline out at some point. But that is what I meant with strategies. So the idea is you could have operated it maybe for a few cycles without extracting the thermocline, without having any temperature drop. And then you need some sort of special operation where you extract the whole thermocline. Then you need to do something with the heat, obviously. But in that case, then you would start off with a fresh thermocline again next cycle. So this would be the other option. Okay. Yeah. And there are some concepts of phase change material at the end. So but this adds more effort to this system.
Any other questions? Thank you, Christian. Questions from the online audience? Otherwise, let's continue. Giuseppe, I think. Right? Oh, no, this is a little one. You want to sit or stand or? As you like.
Okay. Good morning, everyone. My name is Giuseppe Pedroni. I am a technician in ENEA. And now I'm going to talk about some practical technical issues regarding a plant, a facility we have in ENEA. Quite small facility. No, the facility did more than 20 years ago. At the time, the president was Professor Rubia, that wanted this great solar project using solar salts in Italy. And this facility Mose was built to characterize the molten salt, because we didn't know anything regarding this fluid. Okay, this is the facility. The characteristic is the flow rate up to 1.2 per second, the temperature maximum 550 degrees, and the temperature maximum is 3 bars. And after the test experiments, this plant worked to study materials and components of this kind of plants. This is a screenshot of the control system. The facility is quite simple. How can I look at the?
But if you use the mouse, because then also the online participant can see it. That's the easiest with the mouse. Yeah, because then also the online participants can. There's a small laser pointer here.
Yeah,
but
Let's use the mouse.
Better with the mouse, because otherwise the online participants cannot see it.
This is the tank. It's a small tank about 500 liters. There is a pump, a vertical pump inside. This one. This is the outlet of the plant. This is the flow meter. Here we have an electrical heater to increase the temperature of the salts.
is controlled by a system to have a regulated temperature outside. Here, this part of the plant is for some test section we want to study. It's a zone. Here is this component is on an air cooler to decrease the temperature. Here a bypass. And here is the inlet of the tank set. Oh, this is a scheme of our tank with this is some resistances to heat to preheat the tank, the salts. This resistance used also to melt the salt inside. This is the pump. You can say the pump is under below the level of the salts. Here there is another resistance vertical because at the beginning we didn't know how to is the best system of is vertical or horizontal resistances. This is the design of the electrical heater. We use this is a schematic of the component. We use the joule heating system to preheat the pipe. Here are two clamps, electrical clamps, positive pole here, the negative pole, sorry. And at the center there is the negative pole. Yeah, we have some insulated supports because of joule heating uses electricity, so we need to insulate this pipe. This is the scheme of the air cooler, similar to the heater, but here there is a blower, and the salts goes on the piping. Also here we have the electrical clamps for the tracing, and there is an external containment for the flow of the air. Okay, one of the problem with the salts is the need to preheat piping and the components. We use three systems with heating cables. This one principally for the piping, or joule effect. There was a drawing. Okay. Or armored resistance. Okay. This is a common system to preheat the piping. Standard heating cables, a resistive conductor inside, a mineral insulation, and a sheet. Okay, this is how we arrange this cable on the pipe. This is the cable. Is put along the piping, fixed by this kind of clamp. We put a thermocouple here to control the temperature with a plate to the top. And then this is the junction between the hot part and the cold part of the cable. This is another picture. Around this piping with cable, we used to put a metal sheet to protect, to avoid the contact between the cable and the insulation. Otherwise, we risk to burn the cable. Okay, here we can see this part of the cable. Outside will be put the insulation. So the cable itself is covered with a metal sheet to avoid the contact with the insulation. Usually the point to where to put the junction is here between the insulation and the external point. This is a work not very good because best and here the junction, but during the exclusion is not so simple to obtain a perfect work. Here we can see how to trace a valve. Usually we use this kind of valve, Carabello valve with a bonnet, and then best way is to put two different cables. One is the same cable, the piping, so it goes along the pipe itself. And best to put a second cable for the bonnet of the valve with another thermocouple for the control, because when there is the circulation, the pipe reach the correct temperature. So the cable is turned off. This case is a bad mode. The cable is the same. When there is the circulation, this cable is off, it's turned off. So this part of the valve is not traced. So remain cold. If this part of the valve is cold, it's impossible to manage the valve. Because of inside there is a bellow, the salt probably is solid, and we cannot activate the valve. This is an arrangement for the flanges. Cable goes around the flange. This is another arrangement for the vents. In the upper part of the plant, we have to put, of course, a vent. In this case, we have a cable, a unique cable, just one cable, that hit the pipe and the valve, because when we need to open the vent, here there is no circulation of salts, of course, just a circulation of air. So when we need to operate here, we will turn on the cable, and all the parts is heated together. Of course, another thermocouple to control this cable. This is the case of the drain in the lower part of the piping. Usually we have to put a drain pipe. Similar to the vent, the cable is just one with the thermocouple to control this part of the pipe. This is another case of the pressure sensor. We tested in Mose plant this a sensor for the pressure. I will talk about after these slides. And then there is this sensor is arranged in this way. We have a derivation, a valve, and another derivation. Here we will put the sensor. We tested that this sensor worked well. In this case, also in this case, we had to heat this derivation. We can use just one cable. It's a thermocouple. This is the cases for the tracing in a tank. Here in the bottom of the tank, vertical tank. This is the schematic of a Joule effect system to trace. In this case, is a solar field. These are the collectors. This is the electrical connection. For the Joule effect, we saw some problems with the clamp. This is a correct way to link the cable, electrical cable, with the clamps that are welded on the piping. This is the clamp welded on the pipe. It is a plate to reduce the temperature of the heater of the pipe, of the cable. This photo shows how a bad system to push the connection. Here, maybe for the not to the connection not too strong, for the temperature to hide in the clamp, but this cable is overheated, so can create the images here. Other examples of bad arrangement. This clamp are overheated. Here, this can happen straight to the in that case. For the this is a receiver. In this case, we need to insulate this support for Joule effect. So we need to have this in insulation, with insulating material here to insulate all the receiver. Now, this is an example how to put the armored resistance in a tank. We used to have to put a well in the lower part of the tank. A well lets to remove the resistance in case of failure. This is a complete scheme. Inside the well, we put an armored resistance. This well is always below the level of the source. In case in case of a failure of a resistance, in this case we can easily remove it. This is a photo of the Mose tank. We have 6 resistance in the lower level. This is a photo of the external part. This is the resistance, and this is the flange where we link the resistance into the tank. Okay, now I'm going to talk about CS. It was a problem at the beginning because sources are very difficult to seal. Best way is to use the weldings where possible. In this case, for example, for the valve, welding valve are the best solution to avoid leakage of the source. For the gasket, at the beginning we used the flat gasket, flanges, flat flanges, but this system worked better. After several experiments, we found that the best way is to use ring joint flanges. Ring joint something like this. We have a slot where to put this ring joint, and this is the scheme how the system works. Okay. This system worked very well, but we have we must be careful during the maintenance operations when the system is opened. The best way is to change the ring joint and clean careful the slot. Another system for the CS is this kind of fitting, special fitting. That doesn't have this kind of fitting. Doesn't have the gaskets, but there is a metal to metal seal. We have this ferrule, 2 kind of ferrule. This is the pipe inside. The seal is metal to metal. This is with the thread, but it's a bad way for the consult use this thread. The best is have a fitting the solder type terminals.
Up to which dimension do you use these stretch lock type fittings? Up to which dimension? Small ones. I mean, they are usually small ones.
Maximum an inch.
Okay. Yeah.
An inch or an inch a quarter, not over. This is the sensor we tested recently in the Mose plant. This kind of sensor gave good results. This is the scheme. We need, as I said before, we needed to put a derivation from the pipe, of course welded. We have to put, this is an adapter, a special adapter for this sensor. And the seal is metal to metal here. It's a conic, two conic surfaces. Here there is a thread. And the insulation must have to reach this point, not over to avoid an overheat of this part of the sensor, and not lower to avoid a freezing of the salt here. The salt must be melt, of course, in this volume.
Can I ask about the temperature level that we did the test of the sensor up to what temperature?
The temperature,
The maximum temperature of the salt.
the salt, the 550 of the circulation.
But then you have a cooling section to the sensor. At the sensor itself, it's lower already, the temperature, I assume.
We tested also the temperature of the sensor. Maybe my colleague can have the temperature of the experience we did with this sensor. We put here some thermocouples to know. This is the test we did. This is a thermocouple here. This is the adapter, the mechanical adapter of the. We put here a thermocouple here and here. This is the sensor. We have the values, no? During the experiment of this Valeria, do so?
Yes, the reason that cooling system of the transfer.
Cooling system, no. This is the final arrangement. Okay, this is the resistance, the tracing, insulation here until this point. Okay, and then it's free. This is some. Of course, we have to put some degrees for right temperature for the thread. Okay, regarding the valves, we found that the best type of valve are these bellow valve. Here we have here bellow. Here we have to weld. And the actuator is a globe. There is a bonnet. Here is welded. And this kind of valve works well on this. This is some pictures of our Magalli valve with two different cables. One is the bonnet cable, and this is the pipe cable. Okay, I finish. Thank you for your attention. I'm at the disposal for any questions here, or this is my mail, or other questions.
Thank you very much, Giuseppe.
Okay.
Questions?
No question.
Interesting details about your installation, details of heat tracing, welding, sealing,
Okay.
probably of value for many others.
Nobody has a question. I asked something. So, Giuseppe, you also use Joule heating in the lab for small scale installation. I always thought you only used Joule heating for the draft heating, but you also had a small installation of Joule heating for the music plant in small scale.
Yes.
Joule heating. And how long did you operate it, and how was your experience with this Joule heating? Did it work well in Mose, and how long did you use it, and what was your experience in Mose with the Joule heating?
We use it for a long time, for the beginning of the plant.
Okay.
Now we use Joule for the la caldaia, for the boiler, for the to increase the temperature, we use Joule heating.
And the total operation time, how would you say, how many years you operated this, the Joule heating? From the beginning, you said
For
most.
the beginning, Mose didn't work every day.
Yes, of course.
But we several hours. So we now are now is running. For example, we are doing some experience of several hours of 400 hours.
800 hours.
Okay, that's a typical period of testing, I think. But you had several campaigns with over many hundred hours already. Several measurement series for hundreds of hours, yeah, in the Mose plant already. Yeah.
Understand well.
Can anybody help translate it to Giuseppe?
For example, okay, on the model was started at the beginning of the 2000, and we have done during these 24 hours, 4 years, sorry, we have done several experimental campaigns, also especially for the product test. And so at the beginning of 2010, the model was graded in 8,000 hours long.
Okay.
And now, especially in this period, we started on January, more or less, and okay, so now running with another product test of other material. And we have done until now, from January to now, 700 hours of the day.
Yeah, okay, long-term test. Thank you very much. Yeah.
Okay. Thank you.
Any more questions? Any further questions?
Yeah,
Okay.
did you do any like further investigation about the accuracy of the pressure? Accuracy. How precise the measurement of the pressure is?
The pressure.
Yeah. Is it working well? I've heard
This kind of sensor worked well.
Yeah, I've heard the gave one is quite rough, not so for like small pressure.
The range of pressure.
Yeah.
The uncertainty of what?
Yeah.
The range of
Yeah, the uncertainty of the signal of the measurement result. How precise is this center?
the signal, the values not so flat, so continuous. There's a bit of variation. But for this plant, I think it's not necessary a strong precision or
Yeah, okay.
It works well. Don't in the past we used a different kind of system for the mutual system, but it's also we had a lot of problem. Now with a very good solution, simple, compact, portable.
Okay, Giuseppe, thanks once more.
Bye.
Yeah, it's a trick. Also introduce yourself a bit.
So, hi everyone. So my name is Frank Lasing. I work at the DLR and Thomas Bau's group in Molten Salt Research. Today I will talk about molten salt loop, where we increase the temperature to 620 degrees. So, as you all know, the state-of-the-art temperature limit for nitrate molten salt storage is 560 degrees. Usually we have a two-tank system, and the idea is to increase the temperature of the hot tank. In this way, we have several advantages. One is that we have a higher energy density. And the other one is that we can also achieve higher power cycle efficiency. And this leads to overall lower cost. Possible new applications are supercritical steam cycles. For example, if you want to repurpose coal-fired power plants, usually they have high steam parameters, and with this advanced 620 degrees technology, now you're able to actually use it as a heat storage for these power plants, and also ammonia crackers as an example. So the challenges are that first of all you have a corrosion and salt oxidation if you increase the temperature. That's what I will show you in the next slide. And the other challenge is that there are actually no commercial components available yet for this high temperatures for nitrate molten salt. So the first challenge, corrosion and degradation of salt. In this slide, you see there are two basic degradation reactions. So the first reaction is the nitrate to nitrite under the formation of oxygen, and the second reaction is the nitrite to oxides and nitrous gas. If you increase the temperature, these the equilibrium will shift to the right, and oxygen and nitrous gases are constantly being replaced in an open system. So you have a phenomenon called tank breathing when you charge and discharge your tanks. And each time you charge and discharge your storage, air will come out into the system, and also it will extract all the oxygen or parts of the oxygen and nitrous gases to the atmosphere. And this leads to a high degradation reaction for these high temperatures, producing corrosive oxides. And these corrosive oxides, they will form corrosive, they will lead to corrosive attack to the steel. The idea is to have an active gas handling system, which actually keeps all the oxygen and nitrous gases in the system. And this way, these reactions or the equilibrium will be shifted to the left again, and less corrosive oxides are produced, and therefore less corrosion. In lab scale, it could be demonstrated that salt can be stabilized up to 650 degrees with this method. Also, the corrosion rates are well below 30 micrometers per year that could be achieved. So that's the idea of how we can increase actually the temperature the sixth release, please. Now let me talk about the component testing. So we have a project called Limelisa, and the project goal of this is to develop and qualify pumps and valves for molten nitrate salt at 620 degrees. This is done at the DLR, and also one objective is to develop these pumps and valves also for molten lead, which goes up to 700 degrees at the KIT. This project is together, as I said, with the KIT and KSB as the pump and valve manufacturer. We are in the end phase of this project. So the project started with the material selection, material tests in lab for salt and for lead, and then we did a construction of the test loop and also a construction of the pump and the valve. The test loops were built at the DLR and also at the KIT, and the construction of the pumps were done at KSB. And we commissioned this the DLR test rig for component testing, and did also the first commissioning tests. And I will show you about this next slides. So the loop basically is an oven. You have approximately 300 kilograms of nitrate molten salt. We have inserted a pump from the top. We have a level measurement, temperature measurements. We have pressure measurements of the oven. We also have pressure measurements in the tank. In the molten salt loop at several positions. Here only displayed for one position, but we have more. We have flow measurements, and we operate it with two valves. One is used as an on-off valve, and the other one is used as a bypass valve. Also, we purge this oven with oxygen-rich gas to prevent the salt degradation, and this is done through the double mechanical seals of the pump. Also, for a few tests, we need to evacuate the system or reduce the pressure. So we have a vacuum pump, which we can actively control with a valve. So the challenges that for all the displayed components, the pump, the pressure measurements, the flow measurement, also the valves, there are no commercial components for 620 degrees available that are working well. The pump has a motor with 18 kilowatts and a frequency converter. It's designed for a nominal flow of 6.7 cubic meters per hour. The nominal speed is 2022 rounds per minute, but it can also go up to 2,900, which we tested already. And the temperature, the design temperature is 630. The operating temperature is 620. And they guarantee a nominal head of 25 meters. The valves are of globe type. They have automatic electric actuators. It is all designed for 12 bars, and the material selection was done before, and mainly we use austenitic stainless steel and also nickel alloys for KSB use these for the prototype. And for the loop, also we use austenitic stainless steel. So let me talk about the pressure and flow measurement concepts. So for the pressure measurement, state-of-the-art pressure measurements, they use either diaphragm seals with a thermal oil that goes up to 400 degrees, and we also saw these Gaffron sensors in the last presentation. They go up to at least 600 degrees, and they have a liquid metal filling. What filling? Liquid metal. Liquid metal. Yeah, it's sodium, potassium. And we use a slightly different approach, although we also have these gap-front sensors installed. We also we rely on the high accuracy of these conventional pressure sensors that are just shielded from the high temperature with a controlled gas cushion. That's our approach for the pressure measurements. For the flow measurements, usually these high temperatures, ultrasonic flow meters are suitable, but they are not available for our DN25 piping. So we used orifice plate meter run with a differential pressure measurement, and also here we used a controlled gas cushion to shield from the high temperatures of 620 degrees. So the pump specific research interest. Now, one interest, of course, is to have a long run of the pump. They want to test it for at least 6 months. But at the beginning, we also have the question of cavitation. So cavitation occurs mainly for water pumps if the pressure before the pump is too low. And the question that we have is there a cavitation for solid salt? And from the scientist's point of view, we might say, okay, the vapor pressure of the molten salt is actually quite low, so we would not expect much of a problem with cavitation. But we also hear from pump operators that they experience the drop in the performance when they reduce the pressure, under certain flow conditions, and they assume that this is due to cavitation. So to answer this question, we did some tests. Here the methodology also for the planned experiments. First, we have a validation of the flow meter and the entire test loop with water. Also, the pump was tested before it was shipped to the DLR with water. We then did the pump characteristic curves with molten salt at 620 degrees at the DLR, and also the cavitation experiments for solid salt. And that's what I will talk about now. After this, there will follow a period of 6 to 9 months cyclic pump and valve operation up to 620 degrees. And again, to see if there are changes in the characteristic curves and cavitation experiments. We'll do these experiments again. So in this slide, you see, this is how the loop looks like. So we have, this is the motor, we have the pump underneath, we have these actuators for the valves, which are here. The insulated pipe work is here. In this part, there's the meter run, the orifice plate meter run, and underneath there is the oven. So this picture shows actually the operation at 620 degrees. That's the thermal image. Okay. So the first result I show you is the pump characteristic curve for water and for molten salt at 620 degrees. And we see from the slides or from the diagrams that the pump characteristic curve is similar for molten salt as for water. The difference might be explained due to differences in the viscosity and also the density. The same applies for the efficiency. So for the solid salt, we have a slightly higher efficiency than that we measured, or KSB measured with water. And it might also be that there are some measurement inaccuracies, but this is probably not the biggest. For For the cavitation testing, we did some tests at different flows, so at 4 cubic meters per hour, 6 cubic meters, 7. And then we constantly decreased the pressure in the system. The value NPSH stands for net positive suction head, and basically represents the pressure before the pump, before the fluid starts to boil. So in this term, you see that there's P suction, the pressure at the pump inlet, and so we constantly reduce it from ambient pressure to minus 0.85 bar. And what we see is that we have a performance drop. So the pressure of the pump is reduced once we reduce also the pressure before the pump, and this is a very characteristic diagram for cavitation. So we actually see cavitation in the pump. However, we couldn't hear cavitation. So there's a characteristic noise for cavitation in water pumps. And this was also said by KSB, who sell these types of pumps, and they said, no, we can't hear any characteristic cavitation. So this is the reason why we think that it's not steam cavitation. It's more likely that there is only gas cavitation, which comes from dissolved oxygen and nitrous gases in the molten salt. So the last slide is about the error analysis. I did some. I checked how accuracy our flow measurement is, and also how accurate our pressure measurement is. We see that especially for the low flow under 2 cubic meters per hour, we have more than 10% inaccuracy. However, if we have a higher flow above 4 cubic meters per hour, the accuracy is okay. For the pressure measurements, we actually have quite high accuracies. Below for the high flows, it's below 0.2%. So let me sum up. So we successfully operated the first 620 degrees nitric salt test facility. Also, the pump and valve show good performance to date. We demonstrated a high accuracy of the controlled gas injection pressure and flow measurements. And last but not least, the scientist and the pump operator might now actually come to the same conclusion that although we observe a performance decrease due to gas cavitation, it is most probably not harmful to our equipment. So thank you very much for your attention.
Dankeschön, Berg. Thank you, Greg. Questions? Johannes.
Are there any advantages in using oxygen-rich gas instead of nitrogen gas as here?
In the beginning, I showed a slide where we this is actually necessary for stopping the degradation of the salt. So the degradation reaction forms oxygen, and if we in a large system, if this oxygen is always extracted from the system, the degradation goes on and on. If you now stop this oxygen from going out and increase the oxygen content in the system, you will also stop the degradation. That's the reason why we use approach that.
Maybe I can add one comment, because there's always a lot of confusion with the gases because it depends on the salt. That's true for solar salt. But if you work, for example, with high-tech salt, which contains a lot of nitrate, you don't want maybe to have the oxygen, because oxygen will go into the salt and change the salt. So it depends on the salt, but for solar salt, it's beneficial. Yes, it's beneficial to have oxygen to stabilize the salt.
More questions?
Thank you, Freek. Veronica here. I want to ask if you follow the salt degradation or maybe corrosion at some point. I understand that this is not the main purpose of the setup, but maybe you follow these aspects nonetheless, because 620 is not so state of the art.
Yeah, yeah, thanks, Veronica. So actually we do take samples on a regular basis from the oven. So far we just started our experiment, so we haven't analyzed the samples yet, but we will start soon. And the operation time so far was a couple of 100 hours, or maybe below 100 hours at 620 degrees. So we don't expect that much degradation yet, but we will monitor it through salt sampling, and also we analyze the gas atmosphere to see if there are high contents of nitrous gases coming out. For the corrosion, yeah, KSB wants to post-analyze all the components. They will maybe also cut the pump or the impeller and then see if there's corrosion inside the impeller and also the bearings. Yeah, that's interest from KSB.
Okay. So KSB is in the project consortium, or?
Yes,
or not?
so they're actually leading the project. So they are the project leader. Yeah.
Okay. And another question: did you foresee any safety barriers in case of leakage of the pump?
Yeah. So we have yeah. So we have a safety for the nitrous gases for the gas atmosphere. So we measure measurement above the oven, and also for in the case of leakage. I mean, we already had our first leakage, but we fixed it. So we have thermocouples underneath every potential position where leakage might occur, and if these thermocouples show a high high temperature above the threshold, then we will shut down the pump.
Okay, thank you.
But no protection against, so we don't have like protecting windows or something like in the Jesus composite.
More questions? Perhaps other questions to the previous presentation? Organizational questions? So let's head for coffee break. That's also an opportunity to talk, to exchange, to breathe, take some fresh air from planning today. Right now,
You want to the toilet, it's over there. You go out and go straight.
yeah. So for the online participants, we head for being back at 11:15 on time. That's the plan. Let's see. Thank you.
I introduce a bit of work on materials now,
And try to answer the question, what can we learn from laboratory tests, or why do we do material testing? I don't do it myself anymore. We have a team of 7 people in the group in Stuttgart who do, and they do material testing, corrosion testing, thermal stability testing, and electrochemistry of salts, and process development. So I try to give a bit of an overview. I kept this very general because this is a school, it's a fast track school. So I also introduce a bit some general things about salt, thermophysical properties, salt mixtures, quality control, and then finally talk about compatibility. So basically all the topics related to materials with an overview. So I start with
introducing molten salts. So why do we use molten salt? This slide shows an overview of different heat transfer fluids. You can see all the fluids have different pros and cons. So we see molten salt somewhere here in the second column. But if you would ask the question which of the fluids you can store, the table would be very small, because only molten salt and particles are effective media for storage as well. So because all the remaining things have problems, like oil is maybe expensive and pressurized. Molten metal is also typically too expensive for storage. Water steam you can't store directly, or pressurized water storage is limited, or has a pressure vessel. And there are all limitations. So molten salt is a good solution for heat transfer and for storage. Some very basics. The salt is formed by a neutralizing reaction of a base and acids. So, for example, the formation of sodium chloride, as a very simple example, is typically ionic bond, not covalent. There are some salts with covalent bonding. It consists always of a cation and an anion. So, for example, sodium chloride, you have the cation sodium and anion chloride. And then we can roughly distinguish between oxyanion salts containing oxygen and the ones without oxygen are typically the halogen salts, which are of interest. And there are some others, but they are typically not so relevant for the thermal energy storage application or heat transfer fluid application. So in the end, you have a lot of cations and anions, and you can all mix it together, and then we end up with a lot of possible mixture. There's always a lot of confusion about the water and the salt, because when I show the molten salt facility, they always think there's water, salt-water mixture or something inside. So people know typically salt solutions, so that they freeze maybe at minus temperatures. So that's water which contains some salt, but that's not molten salt. Molten salt is anhydrous salt and typically water-free. So maybe there are very, very minor traces of water inside, but we talk about anhydrous salts. Some of them are hygroscopic, which means if they lay around, they have maybe 0.5 or 1% of water, just because they are hygroscopic. Some are very hygroscopic, and then they form hydrated phases, like calcium sulfate, gypsum, but also if you have calcium nitrate, this forms also hydrated phases, so they have contain more water. From the sources, you can have salt mining underground, like shown here, or from Atacama Desert, for example, in the salt lakes, or you can artificially also produce salt, for example, with the Haber-Bosch process, and have some synthetic salt. So there are different sources of salt. So how can you imagine a molten salt? This is a very, very simplified diagram. So you have an anion and a cation. So here in this case, the anion is very big, the chloride ion, and then you have the cation sodium. Maybe I use the other mouse, yeah? No problem. Okay. And then there's some free space, yeah? That's a liquid. It's not like a solid where you have a packed crystal structure or amorphous structure. You have free space, so they're freely moving around ions, basically. And the salt, here's an example of nitrate salt. The typical situation is that you have a transparent liquid, that the vapor pressure is very low, so that's simply done in the oven, and it was cold at the bottom. Then we see solidification. If you receive the salt as a powder, but if it freezes, it's a block. And the advantage is it's liquid over a large range. Also, the salt can react with a lot of things. So the salt chemistry is very important. Salt dissolves a lot of things. And that's, of course, also the problem of corrosion to be addressed always with the salt. I talked already about the vapor pressure. It's typically very low, but it can be, for some salts with the halogen salt, a limited factor that the vapor pressure gets too high, and then you can't use it properly anymore. The viscosity is low. For example, the nitrate salt has a viscosity like water at 560 degrees, and the heat capacity, especially per volume, is high because the density is typically double of the density of water. And of course, we have them in nature, quite a lot of them. And not all the salts, but the ones we typically select are non-toxic, non-flammable, and not explosive. You have salts, they are explosive, but we don't use them, like ammonium nitrate. If somebody asks you, we don't use ammonium nitrate, I always get also this question. So what are the molten salt applications? To give a bit an overview, the most relevant industrial application is aluminum production with the Altero process. There you have electrolysis process with cryolite as a salt, and then you have also quite a lot of processes for heat treatment or thermochemical treatment. For example, the steel is quenched in molten salt. You also do surface treatment of steel by nitrating of with salt. And maybe for your mobile phone, you have a very hard glass, and that's also done with a molten salt process to harden the glass and have some ion exchange reaction, and that's called the Gorilla glass. You can Google it. That's also a molten salt process. It's used for welding processes because the salt wets all the surfaces very nicely. That's for welding very nice, but in practical application, the problem we heard already about the sealing problems. So that's because the salt basically goes in all minor gaps and so on, and it has a very high wettability. For welding, that's being used, but for us, for practical application, that's sometimes also a problem. Salt has been also for decades of interest for the nuclear field, either to reprocess spent nuclear fuel or for the molten salt reactor development. There was a lot of work after the Second World War, and then it stopped at some point. But we see since maybe around 10 years that there's a renewed interest in molten salt reactor development around the world. And typically they focus on halogen salts. We also have molten carbonate fuel cells. There are some larger megawatt type systems being installed already. And then we have molten salt as a heat transfer fluid for chemical reactor, for example, for the melamine synthesis. There are a few thousand reactors around the world molten salt is used in the chemical industry and act as a heat transfer fluid to have a uniform temperature to either extract the heat or add the heat for endothermic and exothermic processes. So there's a long history of 50 years, I would say. And then we have thermal energy storage in the CFP plants with the nitrates. So I come now to the thermophysical and physiochemical properties of molten salt. And I have 2 slides with a list of the most important properties. We have the heat capacity. And I always show the temperature dependency, the measurement method, and why it's relevant. The heat capacity is either constant with temperature or it increases. If you see somebody which reports heat capacity values with decreasing values, that these are wrong values because it's physically not possible. And this is important, especially for the storage capacity. Then we have density. We typically see a linear decrease of the density, which means the salt expands once you heat it up. And then we have properties like thermal conductivity can be positive or negative with temperature. Thermal diffusivity, we heard this before from Christian, can be important for constant heat transfer phenomena like the moving barrier. And then we have the viscosity with a very strong dependency. High viscosity near to the melting point, and then it drops. And the typical correlation is this one. Okay, then if we melt the salt, there's one property, the volume change on melting is important, and the melting enthalpy, maybe for phase change materials is also important, but that's not a topic here. But if you initially do the melting, you need to consider this. I will explain later on the difference between solidus and liquidus. If I show a phase diagram, there's not only a melting point, there can be 2 points which are relevant. And then we have vapor pressure. Typically for nitrate salts, it's not known, it's very low. But for chloride salts, we know the values, they can be found in literature. And then we have the decomposition temperature, which typically refers to the thermal decomposition. So the maximum temperature of the salt can be limited by the thermal decomposition, by the corrosion, or by the vapor pressure. Typically, people also mix up what is the maximum temperature, what is the decomposition temperature, and so on. But we need to look what is really the limiting factor of the maximum temperature. Then some warning of thermophysical properties here. We see here a diagram of heat capacity values of pure salt, potassium nitrate, sodium nitrate, and here also of the mixture. And you see that there's quite a lot of scattering of data, so you need to be very careful about the quality of thermophysical property values. Also, here's an example of thermal conductivity. You can see you can find everything from 0.5 to 0.7, and then people expect 3 digits of accuracy, but that's not the case.
But can you claim which one are the accurate ones, which are the good ones? Your publication?
We did a publication and looked at it, and I would say for the common salt, we know the thermophysical properties and have agreement and did papers together. I think one paper with Venea as well on the properties. So you can find the publication the right, what we think are the right properties. So of course, measuring a lot, averaging a lot will help to improve the accuracy, but maybe sometimes there are also systematic problems. But I would say for the common mixtures, they are known. It's rather for new mixtures, maybe where you have difficulties to find it. Okay. Then about the salt mixture, the first question, why we mix salt at all? So the answer is simple, because the single salt has a melting temperature, for example, here in the very famous phase diagram, of about 300 degrees, and if we mix it, we get a eutectic point at 220 degrees. So this means we can extend our operation window. That's the main motivation of mixing salt and not using a single salt. And then the difference here for solar salt, we don't use a eutectic mixture, but a non-eutectic mixture, which means in the phase diagram, we move to the left and add more sodium nitrate. And then we have one point here, which is called solidus, where the salt starts to melt, and it has a mushy zone here where it's liquid and solid, and then we have a fully liquid salt from about 250 degrees. So that's the difference between liquidus and solidus at this point. And why did they add sodium nitrate? The answer is that the heat capacity is higher of the sodium nitrate, and the costs are lower. So that's in the end the optimization and the compromise of the melting point and the other property. If we add another salt to the system, sodium nitrate, potassium nitrate, for example, calcium or lithium, we can lower the temperature to around 130 degrees or 140 degrees and achieve lower melting points. But then we have to look at other topics like calcium nitrate is hygroscopic, for example, or lithium nitrate is expensive. And you find also information for this mixture and what is really the exact mixture. It's also in literature sometimes a discrepancy, what is really the exact mixture. And then you can even add more salt and mix it further and further, and you get lower and lower temperature. At DLR, we also did once a development where we looked at one mixture and achieved 70 degrees melting point. That's possible, but it also decomposes quite quickly. So the practical systems are typically the binary and the ternary system. So I would say these are the main low temperature molten salt nitrate mixtures which are relevant for the practical application. This is a mixture with lithium nitrate, with sodium nitrate, and with calcium nitrate. The melting temperature is always very similar, and you can see there are always advantages and disadvantages. The ideal candidate, the lithium nitrate has very expensive.
Thomas Bauer, can you hear me? You cannot be heard by the audience. No. Interrupted voice since 1 minute. No.
No, we hear you with lots of cuts.
No, it's still the same. I think it's the microphone. If you can hear me loud and clear, then it's probably related to your microphone.
Aber auch den Lautsprecher von da, sonst haben wir nämlich.
Jetzt tut's.
Ja.
Now it works.
Okay.
Jetzt besser?
Aber stell mal den Lautsprecher auch auf den hier um. Oder ist kein Echo drin?
Nee, jetzt funktioniert's.
Okay, dann lassen wir es so. Dann lassen wir es so. Dann
Never
passt.
change an. Good. You can see something, you can hear something now online?
Yes.
Yes, perfect.
Okay, we continue. Okay, I come now to the topic of molten salt quality control. So trying to go through the whole process. When you use molten salt, so first, if the salt is being shipped, you need to do some quality assurance in the procurement process. And then during operation, we need to ensure a suitable gas atmosphere to design it, and also in operation to ensure it. And we also recommend, and we do it with our plant, to monitor the salt quality during operation and also monitor the corrosion during operation. You can do this by salt sampling and post-analysis of salt. Then there are also ways, but that's still under development, of regenerating salt and maintaining the salt quality once you saw some decomposition. But I think we are still at a rather early stage in this. But there seems to be approaches and means to regenerate also solar salt. once you see decomposition. To show some practical pictures, you see here sodium nitrate with different qualities, and you can see very nice crystals. And here you see already the impurities. Optically, that's 98% purity. That's typically not sufficient. Typical purities are around 99.0% for thermal energy storage application. There are also recommendations about the impurities, what should be added, and what is the maximum allowable level of the impurities. So that's important for lab, not so much for lab scale, because your lab scale salt is pure, but if you work in a larger scale, you need to check for the quality and purity. There are also things like anti-caking agent, that the salt is flowing freely. You shouldn't use anti-caking agent because it will simply decompose once you heat it up, and it has a horrible smell and so on. Yeah, so anti-caking agent is not a good idea. Of course, then it will start caking salt. If you let it lie around a while, then you get the salt.
Was ist caking auf Deutsch?
That means
Hört sich lecker an, aber
verbacken. It means that you absorb some water and it gets like a solid block. Yeah, and the anti-caking agent avoids this, but it makes problems if you melt it. So you shouldn't use the anti-caking agent, and just fill it in quickly enough. So coming to the molten salt chemistry or the nitrate chemistry, so we have the cations and the anions, the nitrate and nitrate, and then we have different reactions. The two important reactions are the nitrate can decompose to the nitrate and releases oxygen. The oxygen is dissolved at low level, and then it will evolve from the salt. We even saw it if you heat up solar salt. You watch it, you can see bubbles and the oxygen arising. There can be also quite a lot of oxygen coming out of your system in the first instance, because this reaction need to be in equilibrium, especially at high temperature first. And then there's a second decomposition reaction where typically it's said that the nitrate decomposes to oxides. The oxide ions will dissolve in the salt. And they typically are attributed to cause the corrosion. And you also see at the same time some nitrogen oxide formation and decomposition. But Frerk already introduced this. There are also other side reactions. So as I said, the salts are rather reactive. They react with a lot of things. They react with CO2 to form carbonates in the salt. They react also with water, maybe not in short term, but in long term to form hydroxides. That's a rather slow reaction, but it happens for steam or water in contact. And then we have things also that chromium, for example, from the steel is dissoluted in the salt. Glass will also react. We know this from filler materials. Often they contain some silicates or silicon oxide phases, and they typically react with the salt. And also in the beginning, people use graphite seals. That's also not a good idea because graphite will react at 350, 400 degrees to form CO2, and then your seal is basically gone. So we saw this idea from Frerk before. If you want to stabilize the salt, we think it's a good idea to close the atmosphere, to not release oxygen and nitrogen oxides, but rather keep them in the system. And in this way, you can stabilize the salt. This has been also published, and you can find the publication, and it has been demonstrated in the lab, not in large scale so far. The largest scale experiment is the one Frerk showed up to now. I think there's no other experiment with solar salt at this high temperature yet. Then some words about the compatibility with solids. So of course, there's corrosion, there are metals, and we need to look at the corrosion. So I only show here now the corrosion with solar salt. For solar salt, we work with different alloys. We can work with low alloyed carbon steel up to 400, 450, maybe 480 degrees. Then we have, there are some chromium alloys, and then stainless steel is the main alloy at up to 560 degrees. There are different types with different stabilizing elements like the molybdenum, niobium, or titanium. Typically also there are carbon enriched at the high temperatures. And then if we have very severe applications with high heat fluxes and so on at receivers, at molten salt heaters, where we have even higher temperature, then sometimes also nickel-based alloys are used in limited applications. You can see here the corrosion, of course, increases with temperature very strongly. That's a logarithmic scale. But the data, they scatter quite a lot. And that's also because the environment, the salt, plays a strong role, how you treat the salt. Is this an experiment in a very small crucible? Is it in a big crucible? How decomposed was the salt? This will all have an impact on the corrosion rate you observe. So the attacking medium, the salt, is very important also to look at how it was treated and so on to if you want to determine the corrosion rate. And then the material itself, the steel, of course, has also different types, qualities, chemical composition, finishing, treatments, and so on. That there's also a big choice on the steel side. And then you can have, in addition, also stresses. That's typically not done in the lab, but in practical application, you also have stresses available in the system. And then you can have things like stress corrosion tracking, for example, if you have additional phenomena. There has been very limited work in the laboratory to address this, but that's observed maybe rather in practical systems if you have an issue with this additional stress. Then we also heard from Christian that we can have molten salt in contact with filler materials. So the potential filler materials of interest for nitrate salts are natural stone. We work with, for example, volcanic rock, basalt. Also of interest are technical waste products like slag, for example, from steel manufacturing. The difficulty here is a bit that in the slag you find a lot of elements inside. And as I said, the salt will react with quite a lot of things. So the question is always, is the compatibility really ensured and so on. And then we have also cost-effective ceramic structures, what we showed here. That's a possible other way, but of course it's more costly, but it's more defined. We can have also different geometries. We have more freedom. We don't have ratcheting, so they have other advantages. So these are the principal options. And in the lab scale, what we can do is to do oven tests with these materials over similar as corrosion for thousands of hours to see the compatibility. And after that, we can monitor our salt and see whether we see some elements dissolving from the filler to the salt. And we can also examine the filler similar to metals and make cross sections and there are specialized methods to look at the different minerals and detect the different minerals and how they change and so on. So there are specialized methods for in metallography for minerals as well. So similar to metals, there's a own site for the different minerals, and that has been also done by DLR. We have looked at the filler materials up to 10,000 hours already in the past. So I summarize, and then of course we can have a discussion and questions. Some messages, maybe key messages about the material research, what I observed over the years. So often the people think only of the material itself, the storage material, but we always need to take it into account that it has some contact to some maybe water, solid gases, metals, and so on. So we need to look at the whole material system, not only at the storage material itself. And then also typically what I observe is that there are mechanical engineers around, they want to select the material and so on, and they think, oh, well, we want to have it in 2 weeks and so on. So, but typically the material research takes time. So that's often a difficulty, that the expectation is that the results should be very quick. And in the end, you need to do material testing, but it's also still important to do larger scale tests. So in order to see whether things really work, because there are always additional effects, scaling effects. That's what we always see. So there's no way that you can go from small to big in one step. Also, one difficulty is the funding of material research, because a lot of people need the material data, want to know it, but in the end, here is our lab. It's still time consuming. it costs some money, and the difficulty is always the finance of the material research. So I hope I could answer some questions of what I asked initially. So what can we use the material tests for? We can use it for the basis of design, of course. We need the thermophysical properties. We need to know how much corrosion allowance, for example, we add on a tank. We need to select our steels and so on. So that it's very, very important as a basis of design. With the material research, we can also extend the operation range of molten salt. We can go lower, we can go higher by other mixtures to find them, to address new application, to avoid freezing in practical applications. Also, it's important for the operational costs. Now we see some difficulties sometimes also in the CSP plants. So if you need to repair and so on, if you understand better the corrosion phenomena and on a material level, this will help to avoid such problems and to avoid repairs and corrosion damage. And finally, there are approaches also to minimize the capital costs. We can use other salts, we can use filler material, as I showed. We can use more inexpensive steels and so on to reduce the capital costs. There's also a contribution from the material level. So I hope I could give a brief overview and hope you have some questions there. Thanks a lot.
Yeah, danke, Thomas. Thank you, Thomas. Just mentioning the information, the slides will be available after the workshop. Dominic or somebody, I suppose, so Dominic will prepare it. Thanks in advance. I'm saying this because also this presentation once more is a very good collection of information as reference material. Very helpful. Thanks, Thomas, for preparing. Questions to Thomas?
This was too clear and too basic. All are experts. Okay.
You can ask later some questions over some sodium chloride on the food or so. No further questions. Thanks. Before Anna Chiara is starting her presentation, just want to mention we are supposed to take a couple of pictures. I suggest we do that before we go to lunch. So after Anna Chiara's presentation, we'll convene here in front of the screen and take a few pictures. Thanks for your understanding. If anybody doesn't want pictures appearing anywhere where Dominic is going to publish it, please let us know and we try to delete you from the pictures. Okay, thanks, Thomas, once more.
Sorry, I have one question. I didn't get how to raise my hand.
Maybe Anna can.
Donat?
Sorry. Yeah, I have one question to Thomas. Just sorry for being late reacting.
Yes. Donat, stell deine Frage, oder was ist sie?
Yeah, okay. Yes, the question is how relevant is the stress damage? So you mentioned that is very little research on this available. So how relevant is the stress cause damage due to molten salt in practice or
I think the simple answer is it's not known. I think whether that's of real relevance or not, because it has been not examined. There's very limited experiment data available on the phenomena. But my personal feeling is there could be an issue to look at. It would be worthwhile to look at. But I don't know work where people have, because the experiments are very complicated to apply some stress to a metal and at the same time have the molten salt, and it's experimentally quite difficult and to do it. So, and if you simply bend something and put a spring or something, that will not help. That's not sufficient to examine this, because typically at the high temperature, all the stress is released and so on, and you don't have the forces anymore and so on. What you need is a steel, and then you need to pull on the steel type, and then you need to do this in the molten salt. And that's a rather difficult experiment. And we haven't done it, and I'm also not aware that some people approach this and so on, but there's not a lot of data available.
Okay, yeah, thank you. That's quite interesting. Yeah, yeah.
Yeah, once more.
Okay. So thank you, Thomas, for your lesson, because it's very useful also to understand what I will talk about, because I try to focus on the modeling of thermophysical properties of molten salts, because since has already
introduce yourself just in 2 sentences.
Okay, sorry. Okay.
Yeah.
I am Anna Chiara Tizzoni. Okay, I'm working in ENEA in a chemistry lab, and I'm dealing with the characterization, the thermophysical characterization of materials for storage, and in particular on molten salts storage. And we are also now studying some modeling approach. That is the aim of these lessons, regarding the possibility to determine the chemical physical parameters and properties of molten salts in general, avoiding all the time-consuming and costly experimental campaign that of course are needed to have all this data. So within a national project, we decided to develop and validate some predictive models based on literature data, starting, of course, from the properties of individual components that will allow to establish some thermophysical characteristic of nitrate and nitrite mixture according to their compositions. So first of all, we performed a very huge experimental campaign aiming to fill the gaps present in scientific literature, and also to obtain a huge number of values that will allow the validation of the predictive models that we were developing. And moreover, we tried to collect all this information, the data and the modeling that we performed in an open source database that is still ongoing, in which we made the results available, and we are now working on this to allow this tool to be opened and very friendly to be used to all the people that are involved in this field. So we decided to start from this list of binary and ternary salts, because are the most common used. So we characterize them regarding their heat capacity, viscosity, and density. And of course, all the experimental campaign and the mixtures were studied in the temperature range that goes from the values very close to the solidification temperature up to the maximum values for their thermal stability. So since this is a lesson, I will report very, very quickly how we measure the properties and how was the approach to model the behavior. I report at the end of presentation all the references, so you can, if you are interested, you can follow our work. So the specific heat, as you know, we measure the specific heat with a different scanning calorimeter. It is possible to estimate the heat capacity of an unknown molten salt with the use of a known heat capacity systems, and we use as a reference high purity sapphire. And here we reported the results of an average value of a lot. When I mean a lot, these are more than 25 repetitions of measurement for each mixtures. I reported also the experimental error, because as Thomas said, it's not so easy to determine with exact value these characteristics. So we try to modeling to predict the heat capacity of a mixture, starting from the values of pure salt that we determined before. And we use an additivity rule that is based on molar contribution of individual components. So a specific heat of a multi-components mixture can be derived from these equations. And here I reported the results comparing the experimental values, the literature data, and our modeling approach. Moreover, we decide also to model some unknown mixture. There are some mixtures that we did not measured. Also thinking of the same rules. So I reported that again some experimental data, literature data in our modeling, and as you can see, the deviation between the model data and the literature values is about 5%. So this we can state that this approach can be very useful to determine the heat capacity of an unknown multi-component mixture without do a lot of experimental validations. So regarding density modeling, we perform a very huge experimental campaign that is very hard to set up in a lab scale. Density measured are performed based on an Archimedean test. These are some pictures of our setup in the lab. So the equipment consists of a stainless steel container where the salt mixture is placed and is kept under air at atmospheric pressure and is heated up. And the temperature is regulated by a controller. And the salt during the test is stirred to be homogenized. And a steel cylinder connected to the dynamometer is immersed. So the weight loss due to the buoyancy effect is recorded. Here are the experimental results of this campaign. And so we decided to try the approach to model and to use this modeling as a predictive tool also for the density characteristics, especially because it can have a very huge effect for practical application, because if you can estimate the density of an unknown mixture, you can also establish some property for design purposes for a big plant and so on. So according to the scientific literature, we tried this approach starting from the molar volume of each component. And so starting from the molar volume, we can calculate the molar volume of the mixtures as a function of the composition of temperatures. I reported only some formulas just to give you an idea. Density is related to the molar volume and to the molecular weight. So given this experimental data that we obtained during the campaign, the density of the mixture can be calculated with this formula. And I reported only some results that we obtained for all the mixtures that we measured. As you can see, the experimental data, that is the blue line, compared to the literature data and the modeling, is quite accurate within the experimental error. So we decided that it was a good approach. And so we move on just to predict also the density of unknown multi-component mixtures using the additivity rule based on the properties of individual components. So here I reported some examples. Here our model is the blue line and the literature data are the red line. As you can see, there is a good, it was a good approach. So we finalized this modeling. Then we decided to determine the viscosity of all the mixtures that we reported with a areometer. we performed a lot of tests on each mixture, just to be sure and just to decrease the experimental error. Here we reported the viscosity versus temperature, and I reported only the very easy formula that, as everybody knows, the gradient of velocity, it is called shear rate, is uniform between the two planes, and the viscosity can be defined as the shear stress on the shear rate. And for the nitrate salts, if the relationships between the shear stress and shear rate is a straight line that passes through the axis origin, this fluid can be defined Newtonian, and the slope of this curve is the viscosity. So once we performed all the experimental tests, we try to simulate, to model the viscosity of unknown mixtures using this formula. And I reported only some results. That is a comparison between the experimental data and the modeling. And as you can see, there is a good accordance for the, for example, potassium nitrate and nitrite, and sodium nitrate and nitrite, and for the solar salt, but not with mixture containing calcium. So for mixture containing calcium, we prefer to use a different approach. And so we consider an interaction between the solute and the solvent in an electrolyte solution that is based on the theory of the liquid state. So here I reported only a few formula, that is the approach that we followed. The viscosity of a pure solvent at a temperature can be expressed like this formula, that is the sum of an ideal mixing and an excess contribution. So it is possible to consider the ideal mixing contribution with this simple equation, where A, B, C are the fitting parameters, and C is the mole fraction of the solute. And we decided that it could be a good approach also because these parameters in the equation have a physical significance and are related to the degree of ionic hydration. So I show you the results for this mixture containing calcium, and the results are more accurate than before. So we stated that they are satisfactory only for calcium nitrate fraction higher than 0.3, and we are still investigating more in details what happened with the calcium. So a few words regarding thermal conductivity modeling. We have an hot wire system in our lab, but for now we can only perform experiments at room temperature. So we decide only to study what could be a good approach to model this property. And we stated that for binary mixture, we can assume that the components of a mixture are mixed in a way that the mixture can microscopically behave as a uniform phase. So the thermal conductivity in a fluid at a macroscopic level can be simplified assuming a flow of it through two types of unitary cells in series. And this phenomenon can be repeated as the sum of all the microscopic levels. So we don't have for thermal conductivity experimental data, but we tried the approach using literature data. And here are the results of the comparison for these binary mixtures. We are sorry that there is a lack of data in literature regarding some binary composition, but we reported this approach because we are going to improve our experimental setup. So maybe we are going to measure by ourselves this thermal conductivity, so we will be able to fill all the gaps also to this modeling. For multi-component mixtures, the approach is quite simple because we can use, as before, this formula that is the sum of the molar composition and the thermal conductivity of the individual components. And here we reported the comparison between the literature and our modeling data for these other multi-component mixtures. So just to sum up all this information, we developed, sorry that is still in Italian because it was part of a national program, but we are going to translate this database in English and to put it online and available for, it will be part of a next project. This database can search all the data that we filled in, can calculate the properties that in the way that I show you using the formula that we defined. And there is the possibility also to insert new data, of course, together with references, and that should be validated from someone. We will see. So we, when we finished this first part of the work, we decided that it should be improved, considering also the data for thermal stability and corrosion and compatibility with other materials. That could be very useful to insert also these properties in our database. So even if our first approach of this experimental and modeling campaign was good because it came to complete missing data and to identify also innovative formulation of mixture that could be used as thermal energy storage or its transfer fluid without measuring them. We decided that we need also other data regarding these two important topics. So here, since it's a lesson, I only report you the way in which we are approaching all the experimental campaign to obtain this data. So why it is so important to determine the thermal stability of a molten salts, because of course it determines the upper working temperature at which the mixture can be used. So it will be very, very useful to have all this data before deciding to use a mixture or another. So just few words regarding the molten nitrates degradation mechanism. It consists of two steps. So firstly, in air, nitrates and oxygen are produced, and this reaction could be reversible. But in turn, nitrates can lead to a second reaction to form the oxides. And this process is not expected to be reversible. In fact, alkaline oxide can accumulate, increasing the melting point of the mixture, can react producing alkaline hydroxide that are very corrosive and also carbonates, and of course can precipitate, leading to problems to valves and pipeline occlusions. So the discriminating point to determine the upper stability of a mixture is of course the thermal stability point. So we set up this heating salt heating system in our lab. It consists of a stainless steel reactor that is characterized by two concentric cylinders, and the internal one is in stainless steel, and it is where the salt is placed. The external one is in refractory material and contains the heating systems. So during each test, we insert the salt in the setup, and the salt was heated up to 3 isotherm values and is kept at these 3 temperatures for 48 hours in air. And during each isothermal step, we sampled the salt 5 times to analyze the salt during the time and according to the temperature. So after each isothermal test, a few grams were sampled, and we investigated by ion chromatography the presence of nitrates, and by acid-base titration the presence of oxides. I reported the trend of the nitrates formation during the time and according to the 3 isothermal values, and also the behavior of the oxide according to the time and according to the different isothermal values. So we are now working on this because, of course, these experimental campaigns in lab are very, very difficult to be carried out. But of course, we have a lack of long-term experimental values, but these data are very useful for a comparison. So we can state some correlation between salt instability and volatility, for example, and we can state which components can have a stabilizing effect, for example, sodium nitrate and potassium nitrate, or have a non-stabilizing effect, for example, the sodium nitrite, the lithium nitrate, and so on. So we are not still able to predict the behavior of a mixture based on individual components, but we are now studying some group contribution and considering them to set up the modeling systems. Just as a comparison, we did some calculation to have a predictive tool to determine for each temperature how long will it take for the formation of a sect oxide percentage. Here I reported a maximum values of 5% formation of oxides, considering a 15 years depreciation of a CSP systems. As you can see, there is the comparison between sodium nitrate and a quaternary mixture containing calcium and lithium and a ternary mixture containing calcium. The green line represents the temperature at which you have to use the salt to avoid or to reach the maximum formation of the oxide in 15 years. It's quite different in the three scenarios. So just to conclude our study regarding the thermal stability that is still ongoing, the sodium nitrate is of course the component that is largely used. We can state that the use of the ternary mixture containing calcium, that is the high-tech XL mixture, can be used in a temperature range that is 240 to 420 degrees, and you can use in this range. Quaternary mixture that contain calcium nitrate had, of course, the advantage of being low melting, but is recommended to be used only in a range of temperature between 300 and 350 degrees. And quaternary mixture containing sodium nitrite does not find application in CSP plants because it suffers of a huge degradation mechanisms. So just few words regarding compatibility test. We performed some static compatibility test in a lab scale. Here, I want only to show you some highlight of our works. We decided to choose some representative steels that are the components mostly used in a CSP plants. 2 austenitic steels, 1 ferritic steels, and 1 carbon steel. And first of all, we decided to perform some static test, inserting the salt in the setup that you see in the picture, and heated it up at different temperature for this duration of time. And then we analyzed the salt, the mixture after the experimental campaign, just to check if there were some metals or some excess of something that could damage the composition of the salt. And here are the pictures of the 4 steels that we inserted, and the same analysis before and after the static compatibility test. Here, this first test was performed with high-tech XL at 420 degrees, and you know that the corrosion mechanism is it's very difficult to explain only in few minutes, but what we are looking at the passive oxyl layer that forms during the corrosion experimental campaign. As you can see, before and after, the layer is very compact and there are no damages or no holes in this layer. So we can state that this for now this test was okay, while we performed the same test with the same kind of steels with solar salt at 550 degrees for the same amount of times. And as you can see also in the picture, when we picked up the steels, and then we perform the analysis before and after. As you can see, we have a lot of how can I say, of holes in the oxide layers. And that states that especially the carbon steel cannot be used at very high temperatures. So moreover, we moved on and we decided to perform some dynamic compatibility tests using a facility that can contain 30 kilograms of salts. And this facility has a huge stirrer that simulates the flow of a real plant. We decided to test the same steels of our lab scale tests with high-tech XL and with solar salt at more or less the same temperatures. And even in this case, it was very evident with high-tech XL. That is this picture. I zoomed the layer between the oxide layer and the steel. And if the structure of the steel is quite homogeneous, there are visible some cracks that where the oxide has spread, but without phenomena of flaking, of surface flaking. But it is not so good for a steel, something like this, because the salt can go inside and crack the steels. The same things regarding the solar salt test, of course, higher temperature. We can see that there are some problems, some little holes that formed that cannot be interpreted as intergranular corrosion, but more as grain boundary intrusion over the time that can lead a very huge crack on the oxide layer, leading to the salt to interpolate inside the steel. So now that these are some tests that are ongoing now in the MOSE facility, we decided to test the same steels in a TRL that is higher and inside the MOSE facility. So here I reported the steels that we chose and the temperature that we are going to use, simulating the cycling of the temperature during an actual CSP plant. And we decided also to test the steel like this and the welded one, because we know that the welded one could be more weak, especially in proximity of the welded line. So yeah, I only have some picture because the tests are still ongoing now, but we created a setup dedicated in a part of the MOSE facility in which we inserted all the steels in the way that they can be invested by the flow of the salt, and we will see what will happening after the experimental campaign. Just few words regarding the compatibility of molten salts with solid fillers. Within the Sfera 3 project, we collaborate with Evora in these activities, performing an experimental validation of a screening procedure that could be feasible to select promising ceramic fillers as storage materials. So we two types of slags that are from industrial waste were considered. The first one, provided by Enea, are made of aluminum silicates, and the other one, provided by Evora, are iron silicate slags. We set up, we created a dedicated setup for this experimental campaign, and the methodology was decided according to the scientific literature. So the experimental test condition, that is the temperature and the contact time, of course, were decided within the project. Here I reported all the data for the first experimental campaign. After all the tests, we characterized all the materials. That means that we characterized the salt before and after the test, and also the slugs before and after the test. Here are the techniques that are microtitration, ion chromatography, and we performed also elemental analysis on the slugs, just to see if they were affected by corrosion or something like this. And only few highlights regarding the results. These are the compatibility tests between molten salt, that is solar salt, and Enea slags. I reported the elemental analysis for fresh slags, the slags in contact with the salt, and of the salt after the experimental campaign. We can state that the presence of nitrites in the solar salt is due to this equilibrium, that there is a formation of the oxide, but is related to the contact with the transition method and possible magnesium leaching. So the result overall concerning slag composition showed that Enea slags were stable enough to be used as its storage materials. And the same experimental campaign were conducted with Evora slags. Also in this case, there is the presence of nitrates in the solar salt after the experimental campaign. Also in this case, there is the formation of the oxide, but in this case, it's more or less negligible. And overall, the consistency of the iron weight percentage before and after confirms the stability of the Evora slags during the thermal compatibility test. So now we are collecting also all this data, and maybe we would like to prepare other experimental campaign, maybe that will last longer than this one. And we will collect all the data and we'll put everything in our database just to create for the first time maybe a tool that could be interactive for the people that are working in this field. So for now, thanks for your attention. If you have any question about this, I put all the references here, but you are free, of course, to contact me, and we will discuss together.
Thanks a lot, Anna Chiara. Another very complex presentation about materials, about lab testing. Questions?
Thank you. I need to do
the chats there are comments, questions.
I have a question. Oh.
Yes.
I'm Maria Elena Gennaro from ENI. And I was wondering if you planned to also assess material compatibility for what concerns stress corrosion cracking, since it is I think it is not it is a topic that it is not it has not been already determined.
You mean our experimental regarding compatibility? That
yes,
I didn't listen very well. If they are still ongoing, or we are thinking about.
If you are thinking about testing stress corrosion cracking susceptibility of metallic materials.
Yes.
Okay.
Yes, we are planning to do this. Yes, there are a dedicated part of our starting project that is dedicated to this field. Yes.
Thank you.
But of course, yes, we have to set up some proper facility dedicated only to these things, because as you know, this test will last a lot of months, so we have to prepare everything in advance.
Okay, thank you.
Thank you. Thank you.
Do you have any intentions of expanding this to other sulfides besides the nitrates, or like chlorides or carbonates, or no?
Okay, yes, okay. The answer is yes. I dedicated this lesson to nitrates because of course nitrate can be used, are most commonly used in CSP application, but in other projects we are dealing with carbonates or chlorides. For example, now we are approaching to build a setup for methane pyrolysis using chloride salts. So I did not report here because it was out of this field, but yes. Thank you.
I have one more comment, because you said the first decomposition reaction is reversible and the second is not. But when we did the work on increasing the temperature, we had a closer look at it, and I think for us we also did publish the paper that it's reversible. Also, I think that the second reaction improved because we did an experiment having oxides, and then we added some nitrogen oxides. And
To
we were
reverse
able to
it, okay.
reduce the amount of oxides. So
We did not perform. Yes, we did not perform this.
it shows that's a reversible reaction. So that also required for the approach that we accelerate the temperature.
And we are now studying we are trying to modeling the behavior to understand which is the right point, or which is the right amount that we have to put to make the reaction reversible.
So it's proven already, it's published from us. So
it's ongoing. Yeah. Yes, it's ongoing. We hope. Yes. That's our aim, just to understand the behavior, so that we will understand which is the right point, which is the right amount, and so we can consider the inverse reaction.
And then the other thing, you showed the stability of the salt and the lifetimes of 30 years.
15 years, but it was just a comparison, just to use the data that we already have.
Because you used the kinetic experiment you did.
Yeah. We made a very simple kinetic approach.
In the end, maybe you can compare among each other, but the absolute values, I would be not so sure, because the kinetics depend very much on the size of the experiment.
Yes.
If you have maybe 10
absolutely,
points, then you see other kinetic parameters. So, okay.
Yes. The comparison was just to use the data that we already have, just to imagine, the formation of 5% of oxide for the mixture that we experimental.
I mean, to compare among each others, maybe okay, but the absolute value.
No, yes, yeah, absolutely.
Fine, yeah.
Also, this work it will be part of next national program, so we hope that we will increase it.
Yeah, but thanks a lot. Nice.
Thank you.
There are also some questions on the chat.
Yeah, who can help transmit them? I'm not sure if we can really respond to them.
I can try to answer maybe later if I have the list of the answers of the question.
Ask maybe again.
Yeah.
No.
We should look into that later on. They were not the questions that I saw were not really fitting to the workshop.
Okay. Maybe
Okay.
if there is a list of questions, I can answer
Yeah.
later. Okay.
Yeah, they were not specific.
Okay.
Okay, yeah, thanks.
Thank you.
Honestly, I'm impressed about the activity in this workshop. I'm impressed how good we are on time. Thanks to all. I'm impressed about the amount of material that we're getting here that we'll later have online available. Now it's time for a good break.